Okay, hello. Welcome to this tutorial on capacitance. Now, again, the books is page 46. However, the latest revised edition is on page 37. So, anyhow, let's get started. So, first of all, back to parallel plate. When you put two parallel plate, conducting plates close together but not touching, you form something called capacitor, where it will store energy. Now, two things you need to understand is that the closer you put the capacitor plates, the higher the capacitance. So the capacitance will increase if the D gets smaller. So you could say capacitance is inversely proportional to 1 over D. Another way to make a higher capacitance is having larger plates, so the area. So in other words, your plate is rectangular, maybe, and then if you increase the area of the plates, you will get a higher capacitance, so it's proportional to A. So we can say then capacitance in general is proportional to A over D. So the other thing, later on they found to increase the capacitance, because there's a limit to how close you can put the capacitance, but you still want more capacitance. So how can you generate more capacitance? Or it's very impractical if you put larger plate, because if you think about building a PCB circuit with lots of capacitors, then if you have large surface area, then it's not going to fit. So therefore, the one other thing you could do is in between the plate. Currently, we assume that it's just air, but if you put material that has a higher relative permittivity than air. Now, air is about 1.006. So if you have, say, for instance, Perspex for like some sort of plastic material, then you might get a 4. Okay, so if you have material in between the plate with a high epsilon r relative permittivity, then also the capacitance can increase. So once again, you can add and say, well, it's also capacitance is proportional to epsilon. Okay, so in other words, C is proportional to epsilon r A over D. Now, there's one more thing. There's something called relative permittivity. Permittivity of free space, or absolute permittivity, which is the combination of epsilon r or naught times epsilon r. So the formula that you should generally remember is that it's epsilon naught permittivity of free space times relative permittivity, which is the permittivity of the material, and times by A over D. That's because in our atmosphere we have a certain value for epsilon r naught. So that's what we can do to find the capacitance. So in short, this is the formula you need to use. Okay, so let's use the next page. Okay, so we now know C is equal to epsilon naught epsilon r times A over D. Do we know all these parameters? So first, we know the area is 0.01, so that's good. And we know the relative permittivity is 2, so times by 2. Now, this permittivity of free space is, you will find that in the formula sheets, is 8.85 times 10 to the power of minus 12. So it's very small. And then divide by the distance between the two plates, and it tells you it's 1 millimeter apart. So centimeter is 10 to the power minus 2, millimeter is 10 to the power minus 3 meters. So put that in the calculator. Okay, there we are. And that comes to 1.77 times 10 to the power minus 10 farad. Now, this is something we do additionally at university or at A level. We don't usually use 10 because we always use so multiples of 3, because as you know, like Leno is 9 minus 9, right? So we can change that, make that bigger, because minus 9 is bigger than minus 10. So if you make that bigger, you got to make that smaller. So that's 0.177 farad, or 0.177 nanofarad. Well, unlikely we're going to buy nanofarad, but all you can do is 177 microfarad. Okay, so so if you're going to make that bigger, actually, if you make that bigger, you're going to make that smaller. So it's actually picofarad. So picofarad. So make that bigger, make that smaller by 3 places. Yeah, picofarad, which is minus 12. Okay, so we usually do that, trying to get the standard form so that it fits into this nano and pico. Okay, so just double checking if the answer indicates true. So 46 in the revision guide. And the capacitance is, yes, is not. So it's, oh, hang on here. I've got something wrong here. So I reckon they are saying it's 17.7. So what have I done? It must be something I've done here. So if I make that small, I need to make that big by 1 place. So that's right. 0.177. I need to come back to you on this one, but the figure is right. We got 1 and a 7 and a 7. So unless I mistype earlier, millimeter, yeah, 1 millimeter apart, and millimeter is 10 to the power minus 3. Let's just double check again on the calculator. Maybe they, no, can't be. So let's try that. I'm just thinking, maybe, I don't know if maybe that makes a difference. Nope, I'm gonna stick to my answers. Okay, so I'll let you know. I'll do the video again if I figure out actually I make a mistake. Okay, I don't think I ever make a mistake. Okay, thank you very much.